EGI compute services. Just this the general housekeeping slide with some information about the conference. So please be muted unless someone gives you permission to speak. You can use the raise hand function to ask to speak. We have some room for questions at the end of the session, but I think we can have some questions after the presentations that we will have, so we can make it a bit more lively. The presentations are already available in Indico, so you can download them from there. And well, this is just some. If you don't see the whole screen in Zoom, just move around. It will appear sooner or later. And if you're using Twitter, please share your impressions with this hashtag EGI 2020 and mentioning EGI infra. So I just get started with the session. So as I said, it's compute services in EGI. We will have like a longer presentation from my side about the EGI compute services. I will just put an alarm clock on me so I don't overrun. And then we will have some experiences from some user communities that are using these services. So we'll have a Rekamount with NextGEOSS experience, Alexander Yakutovich with IDALab, and On with the experience with the ELI NP. And then we have some room for questions and answers. So I get started with the introduction to the EGI compute services. So I hope you're quite aware of the EGI service catalog. This is let's say the whole thing. You see here we have different categories. So we have compute, storage and data, application, security, and training. And today, basically, what we will cover is these three ones highlighted in red. So the cloud compute, cloud container compute, and high throughput compute. And the idea is that these three services allow you to run your workloads, whatever they may be, on the distributed resources on the EGI Federation. So we have resource data centers all across Europe and partially the world. And depending on the service, you can run three different kinds of workloads. So we have containers, jobs, and virtual machines. So virtual machines will be the EGI Cloud Compute, containers, EGI Cloud Container Compute, and jobs is the EGI High Throughput Compute. I will start with the very, very basics, because this is meant for anyone that is interested in the services to learn how they work. So I hope this is not too basic for everyone. So the first one, the EGI Cloud Compute, would be about running virtual machines. And this is normally called infrastructure as a service in most of the, let's say, cloud offerings that you may find anywhere. So infrastructure as a service gives you an API-based deployment of virtual machines on demand. A virtual machine is basically a virtual instance of a computer. You get assigned some hardware, some CPU, some memory, some disk, and you also start some software, basically the operating system. You can control anything there. And you have that virtual host where you can run whatever you may need. And this is done without you needing to go and plug things into physical servers. So you have the API that allows you to create the instances, and those instances are started from a virtual machine image. This is the software that the virtual machine will start at the beginning. So normally it's basically the operating system and maybe some other application that you have. So with this virtual machine image and some context that it's, for example, your credentials, you create the instance where you can run anything. And this instance, when it dies, it will disappear. It will not persist. So if you want to make it to the whatever data you generate to last in time, you need to use some kind of storage. You have the block storage that is like plugging a USB stick into the virtual machine, or you can use online storage, which we have several of these in EGI, and there are dedicated sessions on this tomorrow, so you can learn more about that. So those are the virtual machines. Then we have the containers. This is a different kind of virtualization. In this case, we are going into the operating system level. So what we do here is to create isolated processes or set of processes that don't interfere with other processes running in the host. So this is run with created with Linux namespaces and cgroups features, and it's lighter than a virtual machine, so it doesn't have the to simulate the whole system, so it doesn't have so much overhead. Similarly to the virtual machines, you have a container image, which is the initial software that you will start. You can run, it will run on top of your operating system, and the operating system will allow you to access devices as you configure that. The main technology behind containers is Docker, which is a platform that basically makes it easy to use containers. So it hides and automates all the management process of the containers, to create the images, to start them, to stop them, and so on. And well, it's quite easy to use once you understand how it goes. And with one command line command, you can do almost anything. And it's meant also to be easy to move from development to production. One thing that happens with containers is that normally you have a container, one process only. When you start building your applications, probably things will get more complex, and you need something to being able to manage all the different containers that compose your application and make the things work. So you need some kind of orchestration, and Kubernetes is the main platform here. It's I would say it's the industry standard right now. It's supported everywhere, all the hyperscalers and in the EGI providers. And basically what it does is takes your applications that you describe with a description file, and it will take the containers you say are needed for running your application and place them into the nodes that Kubernetes is running. And it gives you some extra features to make things easy to run. So it recovers if something fails, it provides a monitoring, logging, health checking, and some service discovery. So the idea is that you have the description of the applications composed of several containers, and Kubernetes will take care of putting things in place into the infrastructure. The other kind of workload that we are supporting with the EGI services are the jobs. Basically, a job is a command or a series of commands managed by a scheduler. So it has a clear start and an end, and it has normally lots of restrictions, meaning it's not privileged when running on the server. So you cannot start an HTTP server, for example, and it's time limited. So it will run, for example, for 1 day maximum. So once the period is over, the job has to be finished. Otherwise, it will be killed. And the nice thing of the jobs is that you don't need to manage anything. Just submit the jobs, and the scheduler will take care of placing those jobs into the computing cluster as needed. And you can submit lots and lots and lots of jobs, so you can get large amounts of processing capacity over long periods of time. So here the basic components: you have a job description, and it says basically the commands that you need to execute, and what are the requirements, or the time requirements, or the hardware requirements that you want. That will be taken by a scheduler that will put all the jobs in a queue, and depending on the availability of hardware and your requirements, will schedule those jobs into the computing cluster. So those are the three kind of abstractions that we support into the EGI compute services, and I will now go into the details of each of these services individually. So starting with the EGI Cloud Compute, this is running virtual machines on the EGI infrastructure. So again, this is distributed infrastructure as service powered by the EGI Federated Cloud, which is the federation of the cloud providers of EGI. And what we want to allow here is basically for any research international collaboration to go and execute their data analysis software distributed all across the Europe providers with virtual machines based workloads. This is ideal for things that need to be long running, for example, a server that needs to be up the whole time. So you have a virtual machine dedicated to that. It's also useful for a special software that cannot be easily run into a job, because maybe it's too big or it's too complex to set up and so on. So it's better to have a virtual machine that will just run that software. And here, what we have in the EGI Cloud Compute Service, besides the execution of the virtual machines, of course, we have some extra features that make the federation. So we have the federated identity. You can log in with your institutional account into the service. We have a common virtual machine image catalog. I will talk a bit more about that later. We have different ways of accessing. We have a graphical user interface, but we also have command line interface. We support orchestration, which is quite useful whenever you start to build complex applications where several virtual machines and several components need to go together to deliver the application. And we also have central accounting and monitoring. So for a central place, we can know what's the consumption of resources in infrastructure. And we also can see if the infrastructure is running as it should or not. The different access layers that we have for this service are these three. So the top level one would be the graphical user interface access that is delivered with the AppDB VMOps. This is a web page where you can just go and log in and start managing things. Then we have the federated access where we have the orchestration. And then we have the direct API where you can go directly to the different providers and interact with the OpenStack APIs that are supported there. And all of them use the check-in service for authentication. So you can use the same identity all across the different layers and all across the different providers. So some screenshot of the graphical user interface, the AppDB VMOps. Here you can see a screenshot of myself with some VMs running across different providers. And here you can easily click and create new VMs just with an easy to follow wizard. And it's also integrated with all the features of the federation. So it will be able to understand whether the sites are available or not. It can understand whether the virtual machine images are available or not, and so on. And this is using the Infrastructure Manager Orchestrator, which is one of the orchestrators that we support. We have these two listed here, IAM, Infrastructure Manager, and Terraform, but we are not close to these two. We are open to anything else. But these are kind of the more frequently used in our infrastructure. So IAM is development from the UPV, the Universitat Politécnica in Valencia, and it's able to talk to any kind of providers, OpenStack included. So the EGI cloud is supported, but also commercial clouds. It's using the Tosca standard, and it's quite nicely integrated with the EGI cloud features. So it's able to understand the image catalog and the authentication natively. Then we have Terraform, which is an open source tool from a commercial provider that is also supporting almost any cloud provider out there, including OpenStack. So EGI providers are supported. And this is a bit different approach from the IAM. IAM has a server where you connect and the server will deploy things. Terraform runs on your client, on your laptop or desktop, and has doesn't use Tosca, but a description language that is quite similar to the OpenStack API, but it's still very useful for interacting with different providers in a uniform way. And then we have the lower layer that we had in the slide before, the direct infrastructure as a service access, the direct API access. And here just two screenshots. One is the OpenStack dashboard where you can log in with EGI check-in, so you can log in and manage your virtual machines directly, or you can also use the, for example, this listing the images of one OpenStack project using the credentials from EGI. So you can do also this kind of operations with the command line. Just one comment on how you move software to the EGI cloud. So we have the AppDB, which is an online registry of virtual machines that anyone can use. We call them virtual appliances. It's a virtual machines plus some metadata about the virtual machine. And basically anyone can upload VMs there, and anyone can download the VMs there, and they are available for running on basically at any EGI provider. And what we have inside of this AppDB is the a community level management of the virtual appliances. So every community is able to decide which are the virtual machines images that they want to be available on their providers. So they have an interface. Sorry, no, I didn't have the screenshot. Sorry, I changed the presentation in the last minute. So basically, you have an interface where you say, okay, I want, just to say a few, the CentOS Server 8 and the Virtual Galaxy Compute nodes in my community. And once I select them, they will be distributed automatically to the different cloud providers, and the users will be able to just start them as if they were local. If you are interested in running containers, very simple container applications on the EGI Cloud Compute, one of these virtual machine that we have in the application database is the EGI Docker virtual machine that it's just ready to be started and start running Docker containers. But as I was saying before, if you are running a more complex application with containers, you probably will need or will use some kind of orchestration. And this is what we are trying to provide with the EGI Cloud Container Compute. What we do here is to provision Kubernetes clusters on top of the EGI Cloud Compute providers automatically. And we do that with a tool called EC3, which is also developed by the UPV people developing the IAM orchestrator. And here what we have is the user comes to the Cloud Container Compute, request a new Kubernetes cluster. First, it will provision some VMs using the IAM. So this will spawn a set of VMs with the size that the user requests. Let's say I want a Kubernetes cluster with 4 VMs. So 4 VMs will be started. Then Kubernetes will be started or deployed on top of those VMs and configured so you can just use it. And once it's up and running, you can use the native Kubernetes tooling for interacting with the provider. This is a screenshot of the graphical user interface of EC3, where you can create the clusters. Basically, you just click on this wizard where you select which kind of operating system, how big the different virtual machines composing the Kubernetes cluster need to be, and how many of those you will need. And once that's done, basically you will have a notice saying this is ready, this is your IP, this is the username there, and you have a key for SSH into that IP, and then you can just start using the cluster. This is using Ansible and Kubernetes as a tool for deployment. And one nice thing of this tool is that it's also creating elastic clusters that can grow and shrink depending on the load. So if you can say, okay, I want from the beginning I want just one node, but if the load increases, you can grow up to, let's say, 5 nodes, and this tool will automatically do the creation and destruction of virtual machines as needed. If you want to get software into the EGI Cloud Container Compute, basically we are using the, let's say, the standard ways of moving containers around, which are the container registries. A registry is just a catalog of containers that you can download to use. And Docker Hub is the main registry available. It's provided by Docker, the company. And here you can have public and private repositories. It has official repositories. For example, here it's running the Ubuntu official Docker image. So that's running the official Ubuntu image. It's also capable of doing automated builds. So you can configure a GitHub repository, and it will, whenever you put a change into the repository, it will create a new version of the image. And one thing that needs to be taken into account is that the free account conditions recently changed. So now there is some limitation on how many pull you can do from the repositories and how long the images will be stored there. So it will not be indefinitely stored in the Docker Hub. So this is something you may need to take into account if you are relying on Docker Hub as your main registry. This is a screenshot of this Docker Hub showing some of the images that we have for the EGI Cloud, some of the tools that we have there. Another way of distributing applications, especially for Kubernetes, is using the Helm package manager, which is a way to install applications in Kubernetes. Basically, it's a template engine. So you describe your application with a template, and when you install, you give values to the different configuration values that you have, and it will configure the template and make the application happen. There are lots of templates already available. They call it charts. And normally they are quite well done and have same defaults, meaning that you can kind of trust the template and will run quite securely in your infrastructure. So it's quite nice. Moving to the last service in this talk is the EGI high throughput compute, which is meant to support the execution of jobs into the infrastructure. So basically what you do is you have from your client, you submit the jobs to what we call a CE, a computing element node, which can be, we have two technologies right now, it's ArcCE or HTControl-CE. And this will take your job with a sandbox, which is some small input file that you can provide to the job. And this will move the job to a job scheduler that will eventually make it run into a set of worker nodes. And from the jobs, you can access online storage for retrieving data, but also to put in results back. This is every provider has one of these or more of these computing element nodes, and you can submit directly jobs there. In order to move software or to provide software to these jobs, we have CVMFS, which is the CERN-VM file system, and this is a scalable software distribution platform, and it's able to basically make available whatever software you want in all of the different providers of the high throughput compute service. And this appears as a POSIX read-only file system in the user space, and it has the software manager of your community, of your virtual organization. It's able to upload the software there with an interface. So you upload the software, and then it's made available everywhere. And it has some hierarchy of servers, so it's meant to be really fast when you access the files, because these are also cached at the providers for fast access. So if you want to have any kind of software, you can do it using this CVMFS system. You can also run containers at jobs. There are some limitations here. You cannot use Docker directly because Docker requires root access to run your container, and that's not possible with regular jobs. There are two possibilities, two different technologies that will allow you to run this kind of containers. So one is Singularity, which is, it's kind of similar to Docker. It needs to be installed by the system administrator, but it's meant to be used by let's say, plain users and allow this multi-tenant access to container. It works really good. The only thing is that in order to use it, you really need to have a site that is supporting the Singularity. Docker has a different approach. It's completely doing everything in the user land, so you don't need any kind of root access, and you can even download it as part of your job sandbox. So you can download it, start it, and start the container as a regular user, as a regular process. So it's quite convenient because you can make you will be sure that it will run anywhere. Of course, when you start submitting lots of jobs, you will probably use several providers, and we have a tool to make it easier to do this kind of massive usage of the infrastructure, which is the workload manager. This is based on one technology called DIRAC, and the idea is that you submit the jobs to DIRAC, and DIRAC will take care of submitting the jobs to the different computing elements available on the different providers. It has a user-friendly interface and also API access. You can combine cloud and HTC providers for the job execution, and DIRAC will take care of putting the things into the right place to make your jobs happen. There is some more. There is a devoted session on this on tomorrow, so you can learn more about the workload manager. So one thing that is quite requested lately is the GPUs for running, especially things like machine learning and this kind of artificial intelligence use cases. And we do support GPUs on the EGI compute services, in all of them. And the cloud compute, cloud container compute, and high throughput compute. Basically, for the cloud compute, we have specific virtual machine flavors, that is configurations with GPUs available. We have 1, 2, 3, 4 providers of Cessna, IFCA, ISAS, and NCG Ingrid providers. Right now, making GPUs available, but more are coming in the next months. And with the upcoming EGI project, we will have some more. And we have virtual machine images in the AppDB with the GPU drivers ready to use. So if you start the flavor with the image, you just can log in and do your GPU calculations as you would do it in a normal host. For the cloud container compute, we have a Docker plugin configured to use GPUs, and also the configuration of Kubernetes is ready. So basically, if you start the Kubernetes on a virtual machine with GPUs, Kubernetes will be aware of that, and you can use it directly. And in the high throughput compute, it's also available in some of the sites. And for that, you just need to tag the job as requiring GPUs, and the job, when executed, will be placed in a node with the hardware, and it will be available for your job to be used. Just summarizing my slides, these are the 3 services I've been talking about. So the cloud container compute, cloud compute, and HTC. All of them allow you to use the EGI infrastructure to submit your applications and to run your workloads. For each of them, you have different ways of putting the software in. So for the cloud containers, you have the container registries and Helm. For the cloud compute, you have AppDB. For HTC, you have CVMFS. You have the workload manager that allows you to manage large amount of computational jobs into the HTC and cloud compute services. So this will abstract you from the low-level details of these two. And from all of them, you can access the online storage to permanently store your results or to retrieve data as needed. And all of them are integrated with the EGI federated services, meaning all of them use the same authentication and authorization infrastructure. So you can use the same account everywhere. Central accounting is collected for the different services, and we have monitoring for all of them also. And here I have a table trying to again summarize the different characteristics. So the cloud compute, cloud container, and high throughput compute. The cloud compute, you run VMs. It's quite nice for moving applications that you have already running on your host into the EGI providers. The cloud container compute is running Docker. It's mostly meant for existing cloud native containerized applications. And the high throughput compute, you run jobs, and it's allowing you to run large amount of jobs in parallel. And just as pros and cons, this allows you to have very fine-grained control of everything. It's more complex to operate. Cloud container compute is the industry standard Kubernetes, and it will give you Kubernetes without having to worry about the setup. Although Kubernetes is a complex thing, so you need to learn about it. High throughput compute, the nice thing is you don't need to worry about anything, just submit the jobs and wait for the results. And of course, this may not be useful for all the computational needs. So you may need to look into the cloud compute or cloud container compute if your workload doesn't match the job model. And with this, I'm done with my presentation. So I don't know if there is kind of a quick question, or should we move directly to the next presenter? I guess this no questions. So next would be Hervé that will tell about their experience in NextGEOSS.
Yes, thank you, Enol. Good morning, everybody. So, share screen, present. All right. So, my name is Hervé Comment. I'm program manager at Terradue. Terradue is a company based in Rome. We are a spin-off based back in 2006. We are a spin-off of the European Space Agency. So we are specialists with Earth observation data out of satellite missions, monitoring the Earth. And since the beginning...
One second, we are seeing your, let's say, Google Slides screen. I don't know if you're going for full screen or something like that.
I did start the presentation mode, so I can try again to share from this mode. Maybe it was not catched by Zoom.
Yeah, now it's
better. Okay, thank you, Enol. And so as a specialist of EO data and cloud computing, we are supporting scientists and businesses to make use of EO data. And that's the mandate we had jointly with EGI in this NextGEOSS project that I will present, including the achievements and the results, and talking about Earth observation data processing campaigns we could conduct over the project duration. So NextGEOSS is an EC H2020 project, which is now concluding. It was lasting 4 years. It had 27 partners for an overall budget of about 10 million euros. And the project was, successful in building a solution in support of the Group on Earth Observation, which is an international body coordinating space agencies all over the world, and all the agencies and institutions making use and building on satellite Earth observations. So NextGEOSS delivered, first of all, a European data hub, which is a set of catalog capabilities to federate distributed repositories of EO data. As a unique, and the European Data Hub is now available as a unique access point to the range of EO data providers. People can register. We do also harvest automatically repositories. Then we have developed a set of platform services which are intended for application builders who are integrating EO data and running data processing based on EO data to extract features and ingest information into their models, for example. And these are the pilot applications. We had 14 pilots onboarded inside the project NextGEOSS. And all of these teams and collaborative work was addressing one or the other of the geo global priorities over the agenda for sustainable development, some working on climate issues in the framework of the Paris Climate Agreement, and as well some other use cases addressing topics related to the Sendai framework for disaster risk reductions. All these international initiatives are candidates or current users of EO data, and the mission here is to help these communities to make better use or more use of EO data. So for these pilots, the data production strategies are interesting when they are supported with the use of cloud. All these partners have currently, let's say, a market share, whether they are in a scientific domain. This would translate into they have a research mission and recognition in their role in their domain, or they are more business oriented and they have some in-house capacity. Also, in both cases, they have in-house capacity to serve their regular customers or partners. And so the interest of moving to the cloud here for them is to be supported in investigating innovation through new markets, new studies, and so be supported to expand to capacity to serve prospects, to serve new experiments, or even to serve one-time customers. So here you have an example of the data productions that were supported in NextGEOSS. So, for example, the National Observatory of Athens in Greece was supporting geologists to monitor ground activities in areas susceptible to remote landslides. So this is INSAR interferometric synthetic aperture radar expertise. Armin in France was helping grid operators to get a better knowledge of the local production of electricity by photovoltaic plants. Deimos in Portugal was advising territorial planners with the delivery of customized land use and land cover products by implementing some machine learning over Earth observation data and providing trained models to classify the land use and land cover. Or SATSEN, based in the area of Madrid in Spain, which is the European Satellite Center, providing the European Union with intelligence, was relieving their analysts who need to assess security threats by providing them with automated changes detection alerts based on comparing multi-date satellite Earth observation data acquisitions. So in the NextGEOSS project, to serve this type of use cases, the two partners were TerraDue, my company, and EGI, to provide end-user support, to identify inside the EGI Federation the cloud providers to be used to support the NextGEOSS partners who are developing applications, We did establish service level agreements to serve the needs that TerraDoué was proxying in our mission to help people use of EO data and cloud. We did create operational level agreements for all the use cases that were implemented. And finally, we could establish a quite generic and reusable collaboration framework that is identified as a support for the future. And I will conclude on what's next after this successful project. So EGI is here the infrastructure as a service provider. We made use of a cloud compute. We also made use of a cloud container compute, especially Kubernetes deployment. And TerraDoué is providing the partners with an integration platform as a service named ELIP, where people are supported with APIs to integrate their processors, data processors, build an application which is interoperable that will access remote repositories for fetching data, EO data, and which is packaged to be easily deployed on any cloud, where also some APIs provide access for portals to interact with these processors. And finally, to deploy at scale the packaged applications so that we leverage the clusters, data processing cluster on the cloud. So the key return of experience from NextGEOSS was to make data processing algorithms scalable and portable across cloud providers, directly accessible in a standard way. We got web applications more robust in exploiting Earth observation data sources. We built applications where the built applications were based on interoperable distributed systems. And the partners benefited from standard integration layers overall, where they could focus on their core business and be relieved from the technical aspects of EO data and of cloud. So for this, they are delivered on ELIP to build and package with cloud sandboxes. So this is our own private cloud infrastructure here. And application frameworks. So currently people for the project NextGEOSS, let's say people were using our framework based on Hadoop. So it was for them, it was about integrating a processor as a mapper and reducer workflow. And then we would deploy the resulting application package as a scalable Hadoop cluster on a EGI cloud provider. Another return of experience for the deploy side of the operations was to make cloud-ready applications available as cloud appliance on the platform repository of ELIP. And then partners could decide on their cloud appliance access conditions. Are they available only to their organization? Are they shared with partner organizations? Then they could leverage deployers on ELIP that were set up by TerraDoué for the partners to, according to their cloud provisioning arrangements. I will detail this. And the partners were supported in adapting their cloud deployment strategies for the data production campaigns they had to run over the duration of the project. So this is where the ELIP APIs meet EGI and the cloud providers of the EGI Federation. We have cloud controller APIs where we connect to the standard cloud provisioning, cloud IS interfaces. We had followed last year the migration of the EGI providers to OpenStack. So this is now very well standardized over the full federated resource in NextGEOSS, and our deployers to run the operations before a data processing campaign. So this is a view of the 14 partners and their different areas of expertise where they had defined integration needs. Yes.
Yeah.
Okay. I'm at nearly 9 minutes, so I'm about to conclude. So they were developing applications, algorithms, processors. They were identifying data needs, data ingestion needs. and all of them, nearly all of them, could be progressed to be production ready over the duration of the project. Some of them are using the ELIP tools, and a few of them, two of them, DLR in Germany, the German Space Agency, and CLS in France, were using directly the EGI Cloud resources because they had already tools in-house for managing Dockerized applications, and they could deploy this directly on the provisioned resources or be supported to deploy on a Kubernetes infrastructure for CLS and the Mindrift application. But this is the overview of all the deployments over the federation, federated cloud providers. So the ones supported by Terradue ELIP to integrate on our application framework, and the ones who were guided to directly access their provision resources for Docker or Kubernetes. This is a quick summary for the description of all the instances that have been provisioned for them, different technologies, different types of clusters, some of them running more than one application. So they had 2 processing clusters here for Armin, and a budget allocated by the project, which was managed as in a kind of a pay-as-you-go approach, not fully automated, not yet, but as 4 years ago when we started, it was a key milestone to engage into this approach. So you have the summary of the total resources consumed in support of these data production campaigns in NextGEOSS for a total service cost of nearly 100,000 euros for the 4 years of the project duration and the 20 applications that have been run for data production. So the last slide is the conclusion on the key achievements, where we could solidify together with Terradue and EGI, the EGI Foundation as a neutral broker for an expert advisor on the selection of providers, improved the EGI service provider to understand cost and provide pricing for their services, help mature the processes and procedures for pay-for-use approaches. So it was quite innovative thanks to this effort in NextGEOSS. New funding models were developed, and we could make use of a lot of hybrid cloud capabilities for serving all these partner needs in the project. So I'm looking forward to hearing from you. You have my contact details here.
Thank you very much, Hervé. Nice talk. I don't know if there are any questions from the audience, Hervé. Come on, don't be shy. So I have one that I just pop up my head when looking at the list of the resources and the budget. Did you ever did a comparison with let's say the cost of a commercial provider for doing this similar kind of usage of resources?
Not something very formal, but we could see that the main alternate source for us was, of course, from the Copernicus DIAS, the data access and information services promoted by the Commission for the EO data, especially the Sentinels, the Copernicus Sentinel missions. The price lists are quite not yet harmonized, or it's. I mean, even for experts at Terradue, it takes some time and effort to make a one-to-one comparison. But I would say that with this approach, we could see the competitiveness or the potential competitiveness of EGI cloud providers in terms of user need satisfaction, the flavors that were available, the customization of the cloud compute capacities, and even the offering of Kubernetes, which was quite absent at the time from the DIAS providers. So I can only answer your question with a general statement that the cost model and the cost for using EGI was quite competitive compared to the other European providers.
Okay, thank you very much. There is also a question from Tiziana. There is, how will the NextGEOSS activities continue in the future?
So we have established a community inside the group on Earth observation, GEO, which is NextGEOSS. So a little tweak of the name of the project to still be identified, but still highlight the transition. And we will support all the application integrators worldwide who are interested to follow the tracks of NextGEOSS. And this is already established as a formal community in the GEO work plan. So this is a primary contact point for any interested parties to get in touch with us, and we can discuss the modalities for the next steps. So that's the flagship after the end of this EC project is the NextGEOSS, EOS, community activity on the group on Earth observation.
Thanks. I think I can also speak, so maybe I can interact live. Thanks for the presentation. My last question is how the NextGEOSS community is positioning itself with regards to Destination Earth. We will hear from the European Commission tomorrow about it.
I will learn about it tomorrow. I didn't. I'm not aware of this initiative.
Okay.
Is it part of a bigger framework or?
It's part of a framework, yes, that will be funded through the Digital Europe program, which is different from Horizon Europe, and has as an objective capacity building. In our understanding, this is including infrastructure, platform, and software as a service and data. So we see relevance of the different activities, and we know that specific use cases will be prioritized, like disaster mitigation, environmental protection. This is one. But okay, I think we will stay tuned and wait until tomorrow. Thank you.
Very good.
Okay, thank you, Hervé. Thank you, Tiziana, for the questions. So we move to Alexander Jakutovic, who will speak about EIDA Lab. Now we can see you. So, floor is yours.
Yeah. So just one moment, I probably need to start the presentation first, and I will be able to share it.
Okay, I will back you when there are 2 minutes left. Okay.
Well, actually, I have a stopwatch here, so it's fine. So, do you see my screen fine?
Yeah, we can see it.
Okay, perfect. Yeah. So, good morning, everyone. My name is Alexander Jakutovic, and in this presentation, I'm going to speak about EIDA Lab. So yeah, here in the PFL, we develop this infrastructure or ecosystem for developing, executing, and sharing scientific workflows. But before I start the introduction to the service itself, I would like to, give you a global overview how the science is evolving, and this will also allow us to motivate the creation of the service. So now, again, looking globally, we have kind of three pillars of science. One of them is let's say the most ancient one is experiment. So, and this part is mostly done by experimentalists. Then we have the second pillar, which is theory. So, in order to understand the nature, we need to create some mathematical models that describe it. And this part is mostly done by theoretical and computational scientists. And the last part, which has emerged recently in, let's say, last 20, 30 years, is the simulation that is mostly done by computational scientists. And this is the status quo, and we would like, with introduction of EIDA Lab, we would like to change it in a way that the simulations are not foreseen as the only place where computationalists work, but it can be seen as a merging point between theory and experiment. So the experimentalists can use the simulation tools to compare the results with the experiment, while the theoretical scientists can use computational tools to predict the outcome based on their theoretical models. And this already brings me to the motivation. So this all started with the AIDA, which is essentially the tool that we've developed for computational scientists for ourselves, that is capable of running complex workflows, because essentially now, with the modern development of the science, it's typically not enough to run one code. Typically you have a set of simulations that you need to perform, one dependent on another, in order to arrive to the final property that you would like to have. In addition to the automation of the workflows, it also stores the data. So AIDA will launch the simulation and will also store the selected data, and also store the data provenance. So if you, let's say, come with a certain property, you can go back in history and understand where this data are coming from. And it also has a Python command line interface. So obviously that was a great tool for computational scientists, because we can automate many things. But the problem here is that essentially this is only for computational scientists. But we quickly realized that since we have those automated workflows, we can share them with the more general community of experimental scientists as well, including experimental scientists as well. And we can provide a user interface that will allow them to actually use AIDA or the workflows that have been developed. So it is fully integrated AIDA. So now I'm talking about AIDA Lab. It is fully integrated with AIDA. It provides a user-friendly web interface through Jupyter notebooks and widgets. It allows for easy application development, because again, it's Jupyter, so you essentially develop web applications in Python. And it allows for, it provides a collaborative environment and some handy visualization and editing tools, which I will show you later how it works. And finally, it provides the App Store, where the computational scientists can put their application for, to compute certain property or properties. And experimental scientists, or the ones who just want to use them, can install those applications from the App Store and run the simulations without actually need to, to learn the theory behind it. So this is how AIDA Lab looks like. This is the home page. And as you can see, the first application is visually different. So all those rectangles are the application that installed. One can move them, also install and install. And the home application is visually different from all the others. So we have the home app. You can access the file manager. You can have the standard Linux terminal. You can see task manager, application store, that one I mentioned previously, and you can get some help if you are stuck. And finally, to add here is that essentially all of these applications, they are tightly bound with Git. So essentially, if you create a Git repository and you put it on GitHub, then you can register your application on our application store, and our application store tools will automatically detect whether there is an update. So if you if you make a release of your application, you add a new Git tag, then our tools will automatically detect that and will notify the users that there is an update available. So this whole infrastructure essentially allows you to, to create application, to share it among the possible users. Then also just a side note. So we have recently submitted a paper, and just yesterday I got to know that the paper has been accepted in Computational Materials Science Journal. So there we describe the philosophy behind. So we describe the platform. We show the key components, the design of the platform, and the distribution. We show what are the ways that you can install AIDA Lab. And we also show some use cases, like how AIDA Lab can be used in the real life. So, like computing electronic structures of graphene nanoribbons on surface chemistry, scanning for microscopy. And if you need a preprint, it's available here. Then, next slide, I'm going to show a quick video that will demonstrate how a person who would like to use AIDA Lab can actually profit from its interface and from essentially the workflows behind. So here I'm not showing how to submit a calculation, but I'm actually showing once you submit a calculation, the results will be stored automatically. And then what you can do, you can browse them. This is, for example, what we do here. You can click on Show Button. And this, again, this is underneath there's Jupyter. So what we did, we added this mode tool that will hide the source cells and will only leave you with the output results. So this is pretty interactive, as you can see. So here we show the electronic properties of the molecules of the graphene nanoribbons. So you can select the band structure. So you can select the band, and you can see that the track 3D view adapts accordingly. And yeah, so also spin density. So this way, again, this is all Python, right? So you can develop such an application pretty easily. And we provide a set of little tools that will allow you to make those visualizations. So you don't need to write visualization code. You just call those tools, like for visualizing the molecule, and then they will do their job essentially. So here I'm showing how to project and to plot projected density of states. For those of you who are familiar with computational science, you may know that actually, if you would do it in a standard approach, it would require a lot of time. But since AIDA, again, stores all the steps and stores the information locally, then this information can be then retrieved and presented in a nice way, as you can see here. All right, so this is already pretty much it. So what I would like to show, I have a few slides left. So essentially, what I hope I demonstrated that AIDA Lab provides an environment where people with different expertise can collaborate in common computational projects. So you can have computational scientists that develop the workflows and maybe debug them, and you can also have the experimental people that can actually use those applications that were developed by computational scientists, and they simply upload the structure, click a button, run the simulation, and that's done. So you also save time and avoid mistakes because you don't need to present your data in a special way. You don't need to make presentation, because if you both work on the same AIDA Lab interface, you're already familiar how the data is shown, how the data are stored, and this allows you to avoid mistakes, conversion from different units to one unit to another, and all these kind of things. And finally, the modularity of AIDA Lab allows you to build those applications pretty easily. Again, you don't need to write the code to visualize the band structure. We have already a tool that says, give me the band structure, and I will visualize it in a nice way. And we hope to add as many, we hope to continue adding those tools, and also, grow AIDA Lab beyond the material science where it has been developed so far. So finally, a few links. So about AIDA Lab, you can see on materialscloud.org. Since AIDA Lab is under umbrella of Materials Cloud, Materials Cloud is a big platform for where computational scientists can upload their results. They can upload their AIDA databases. They can also visualize them in a nice way. Well, AIDA Lab is as a sub-branch. Is a platform where actually the people, the non-experts, can log in and can run simulations. We have this GitHub organization, so if you are interested, you can have a look. We have the preprint available, that one I already mentioned earlier. And we have open AIDA Lab demonstrator that was set together with EGI, so that has been set on top of Kubernetes cluster. We're still let's say in a testing phase, because there are some issues that sometimes it doesn't work as we expected. So we're still investigating that. And if you'd like to get in touch and learn more about AIDA Lab, please contact us at the following address. So this is the developer teams. Here we have AIDA team, Materials Cloud team, and AIDA Lab team. So I would like to thank them all. And also I'd like to thank the funding and the support agency for their contribution to the project. And I would like to thank you all for your attention. Thanks.
Thank you very much, Alexander. I don't know if there are any questions from the audience. I have one. How is this to, let's say this is quite focused on material science. Let's say, how easy would it be to support applications from other domains? Is it possible? Or?
Yeah, exactly. So now, we're showing example from material science only because it has been born in material science community. So, and essentially, we are thinking to explore, first of all, more domains of science, like going to bio, or going to climate prediction, all this kind of thing. But they all have certain things and certain problems that we would like to face first. And maybe we need to have face them on either side first. Because, for example, if you work with climate, you typically work with a huge amount of data, like terabytes of data, and those things need to be addressed first. We already have a schemas how we support this kind of modes, because again, AIDA typically what it does, it takes the data from the computer, it puts them locally. And when you work with the terabytes of data, you cannot do this. You need to either have a link. So let's say you have a data node in your AIDA graph, in AIDA database, that says, okay, my data are there, and this is how they look like. Or you just need to extract the relevant pieces of your data and store it locally. So that's kind of the discussion that's already going on. And of course, everybody else from different domains of science, or I don't know, who can see the potential of these tools can contact us, and we can see whether we can help them with their tools and publishing their tools.
Okay, thank you very much. I think given the time, we should...
We're 7 minutes left, I guess.
Yeah. Well, Giuseppe, you raised your hand. I don't know if you have a very, very quick question. You can speak, Giuseppe.
Yeah, sorry. So thank you, Alexander, for this presentation. Very interesting. We know that we are supporting this use case in the EOSCAR by the Docker programs. So we are very, very well interested to make this available also in our infrastructure when this collaboration is done, so after March. So for sure, we would like to maybe discuss this offline, because EGI is running an application on-demand services for targeting a user with limited computing capacity, and probably this is another possible solution that we can offer to our end user. So I see some rooms for collaboration in the future. So
yeah, sure if you want, we can probably set up a meeting and discuss a little bit more in details.
Yeah,
I would be really. Yeah,
thank you.
Yeah, I will move to the next one. So I think you got the contact, Giuseppe, so you can contact offline to Alexander. So Janfu, that's your time. We're at I guess it's okay if we just overrun a bit to the coffee break. So the floor is yours.
Hi, let me share my screen. Hi, could you hear me?
Yeah.
Yes. Today the presentation is much on a specific very specific use case of the grid for the simulation of high-power laser experiments. So the experiment here is performed in the ELI, Extreme Light Infrastructure for Nuclear Physics, and ELI is a European project, and first was initiated by Gerard Mourou, the Nobel Prize winner in physics for 2008. And there are actually 3 pillars of the ELI across Europe, one in the Czech and Hungary and Romania. And in Romania, the study is mainly on the nuclear physics. So I will introduce a little bit on the high power laser that we have here. And basically we have 3 types of high power lasers, 100 terawatt, 1 petawatt, and 10 petawatts. So with these petawatt lasers, you can shoot into the, you can shoot into the gas or make it interaction with the solid or any proposal that you want to propose, and to generate a radiation source. But before you doing the experiment, you need you need the simulation to predict the outcome and the direction to design your detector where to look at the thing that you want to see. And by this way, you can save a lot of cost rather you try and error building a detector, but you cannot see anything, and then you change, and that costs a lot. But with a simulation, you can do like in 1 day a few simulations to optimize the thing that you can see. And basically for this type of laser simulation, there are a few codes to do it, hydrodynamic code, particle code, or the particle in cell code. But in this talk, I will specifically go into the particle in cell code. So basically this code is to simulate the plasma, which means if you see here, it's actually all of this you see actually is the electrons, and the ion is stay in the background and a laser propagating through this plasma. Basically, in reality, you cannot simulate everything or every single particle. This is not possible. Instead, we make a kind of approximation, and this approximation is implemented in the particle in cell code. So I'm not going very detailed on the simulation things, and I will briefly talk about this approximation. Is that we introduce kind of simulation particles to represent a number of real particles, and we assign some shapes to these simulation particles, and then put into the physics or the algorithm loops. Even though we have used this approximation, we still need to perform a very large number of data, and it is impossible to do it with a few cores, and we need to parallelize it and distribute into hundred or thousands of cores, and this can be submit it to the grid or any HPC cluster. So the way we parallelize this simulation is that, for example, we split the simulations into a different part, and we put this part into a different CPUs. So during the simulation, you need kind of data transfer between the CPUs, because if you see the electron inside here, it will cross from one side to the other side. So you need a kind of a platform to make this communication, and this is managed by the message passing interface, MPI. So MPI have a few, and the most common one is Open MPI, which is open source, and the one from the Intel's. And both of these is support for C++ and also Fortran. So in our use case on the grid, we are using mainly on the code Epoch, and this code is developed in the University of Warwick in UK, and it's written in Fortran, and it's already parallelized with MPI, and it is open source. So this is an example of the code, how the parallelization works. So in the Fortran code, we call the MPI, and then we initiate the MPI. After a certain initial condition is set up, we broadcast the data across different CPUs. And then during the simulations, we can perform the operation, for example, reduce the data for the output purpose, and also many other MPI functions. For example, you send the data from here, or you receive the data from the other part. And this MPI, you can use it not only in these type simulations, any simulation that can be parallelized by the MPI can be used for the grid. And for the introduction of how to do this, I think for me, this book is quite easy to start with. So when we have all these initial conditions set up, we set the number of CPU that we want to send, and then we send a job and let the grid do the things. And we just sit back and get our data. So you can study the laser interactions with mirrors coming here and bounce back, or you can study with a curved mirrors, or you can study the laser with the gas, or combine the gas with the mirrors, and even you can go to a three-dimensional simulation, and you can add different kind of physics to, for example, to produce the radiation. For this, you know how you should set the detector and where to detect, and the energy range, angle range, and so on. So in summary for my talk, or some example of the use case, so the simulation is needed in designing the experiments. So when we have the pairized code, we send it on the grid, and we can add a different type of physics, whether the physics is already founded or is a proposed of a new physics. We can study it, and we can optimize also the outcome of the thing that we want before we set up the real experiment, and this save you a lot of money. Thank you.
Thank you very much, Yanfu. We are running a bit late, so I think there is not much time for questions. So I mean, we need to close because
Okay, sure.
The next session is coming. I invite you to come to the next session on the compute clinics, and if you're interested in keeping hearing about the EGI compute services. So next will be the EGI Cloud Compute and EGI, the EGI High Throughput Compute with ArcSI. And that's available in the Indico. You have the Zoom rooms, which are different from this one. I would like to thank again all of the speakers. Thank you very much for keeping the time. I know I was the main guilty in being late, and thanks for the wonderful presentations. And yeah, I think we can close here. Bye.
Thank you, Enol. Bye.
Bye. Thank you.